So today's problem is called count number of nice subarrays. Before even I start reading the description of the problem, first of all, I would like to make you or explain you another problem called subarray sum equal to k. Right. So now we're not like looking at the main problem right now. We're looking at we're looking at another problem called subarray sum equal to k. So let me explain what happens in that problem. And we are also looking particularly look at a variation of that problem in which we are trying to find the subarray sum equal to k when the elements are either 0 or 1, right? So for example, suppose this is an array and this has only elements which are either 0 or 1, and then we are trying to find the number of subarrays in this array which sum to a particular number k, which means that in a way number of subarrays in which number of ones is k, because anyway 0 won't contribute anything to the sum, so number of ones is k, right? And in order to explain this problem, I'll go through a few steps, right? And then just hang with me while I explain those steps. And at the end of the explanation of those steps, it will be pretty clear why those steps are required. And all those steps would obviously lead to solving this problem in an optimal way. So what are the steps? What are the steps? The steps are, first of all, we need to keep a prefix sum accumulator, right? So basically, if we are at this index, our prefix sum is 1. If we have reached till this index, our prefix sum is still 1, because prefix sum is basically you just keep on adding the current index value to the sum. So this is 1, this is 2, and so on and so forth, right? So this is how we calculate the prefix sum. And then once we calculate a prefix sum at a particular index, so prefix sum again is the sum starting from the 0 index to that index. We also store in a particular data structure the index at which that prefix sum was being computed, right? So suppose, so how would the map look like till here? So for prefix sum 1, we got this prefix sum at the 0 index as the 1 index, and for prefix sum 2, we only got this prefix sum at the 1 index. So I just wanted to I mean uh, I mean divert your attention, or I want to focus your attention on one particular thing here, that the prefix sum always keeps on increasing, right? So for example, for a prefix sum of 2, we'll always find indexes for prefix sums which are less than 2. For example, here there is only 1 here, which are which those index so the list that that particular key contains, which whose key is less than 2, key being the prefix sum, the corresponding value vector here of this prefix sum will always have indexes less than the index that this 2 contains, because the prefix sum is increasing, right? It's not strictly increasing because we have zeros in between, but it is increasing, right? So this is one particular attribute that I want to that want you guys to focus your attention on. I'll use this later, but this is an info for now. For you, I'll be using this later. Okay, now let's move on. So what is this prefix sum for, right? Because as I said earlier, I'll be using a few steps to compute this subarray sum equal to k. What is, so and then I'm suddenly computing a prefix sum, maintaining a map, right? So this is kind of a map, right? So value is the prefix sum. Pardon me. The key is the prefix sum, and the value is basically the value vector is basically the indexes where that prefix sum uh, happened. Now, what will you do with this, right? So for understanding what is the use of this, let us come to this problem that we have, right? We are trying to find subarrays which have uh, running sum or the total sum in the range as k, which also means that the number of ones in the subarray is k, right? Suppose at index I, we have a prefix sum of pi. This is the entire array that I have. And at index j, we have a prefix sum of pj. And now sitting at index j, I want to figure out how many subarrays are there whose uh, whose range sum, cumulative range sum is k, right? So what we'll do is that we'll look for pj minus k. We'll look for pj minus k in this in the map that we generated, right? So since we have pi at index I, so in the map there will be one value which will have key pi, and which will point which will have I as one of the elements that is there in the vector, right? So if there are like zeros here, I plus one also will be here, right? Suppose there is 1 0, so it will also contain one I plus one, right? Because since it is 0, so the prefix sum has not increased even at the I plus 1th index. So I plus 1 also will show up as one of the values in this map, in this list of values, right? And then it happens so that pj minus k equal to pi. What does it mean? This means that this entire subarray, right? This entire subarray has got a range sum as 1. Right? That is what it means, right? And then this is what means for uh, so so pi has this map has got various elements. This so so it has various elements for the for just referring to the ith index here, which is one of the values in the list. This particular subarray has k ones, or a running sum of k, or a range sum of k, whatever, however you may say it, right? And obviously this is a 0, right? So what does this I plus 1 represent? This I plus 1 represents that there is another subarray starting from after this 0 value, which is at I plus 1th index, which also has a subarray sum of k, right? So that means the number of values that exists in this map corresponding to the key pi, given that pj minus k is pi, that number of subarrays we have found, right? Right, with the with having running sum, range sum, or subarray sum as k, or the number of ones in the subarray as k. So this is this concept, right? And there is one more small caveat that I want to mention now. What is the caveat is how we are populating the map, right? So we always start from the first element, we pick this up, and then basically suppose this is 1, so a map of 0 would be equal to 0, right? Pardon me, map of 1 would be 0, because we have prefix sum of 1 at 0th index, right? That is what it is. Now there is one more scenario. So note one thing, that we don't have zeros in this map, right? We might not have zeros in this map. I mean, uh, uh, let me rephrase what I'm trying to say in some other way, and also use a diagram to show what I'm trying to show. So for example, if we want to capture a situation in which the prefix sum, that is the range sum starting from the 0 index to this jth index, that itself is equal to k, and then what we're trying to find, we're trying to find like pj minus k. Suppose this prefix sum is pj, so pj minus k in that case will be 0. That means we need to find 0 in the map, right? But that particular relative thing is not there in the map. What I'm trying to say is, for example, you saw that prefix sum till ith was something pi, and then that means that after I start from the start, there is a start index which starts after I and then ends at pj. That means start will be I plus 1, because prefix sum prefix sum was pi as I, and then pj minus pi is equal to k. That means the index after that, starting from the index to the jth index, we have an array, right? So that means we need to our pj minus k should be uh, equal to a value which is before the starting point of the subarray which sums to k, which is trying to represent, right? I hope you get this point. But beyond zero, there is no such subarray, right? Beyond zero, there is no such subarray. So looking at this map, there is no way to figure out whether uh, uh, looking at this map, there is no way to capture this particular subarray, right? There is no way, because there is nothing beyond this. This is like -1 index, or this index is beyond bounds. There is no value for this, right? Maybe we could in the map we could have put a value like a map of -1, which is an impossible value equal to 0. Then we would have able to capture it. But there is no such value in the map. At least we did not put it. So what we will do is, whenever we found a prefix sum which is directly equal to k, we'll just consider that we have found an array which satisfies our criteria. That is there is also a subarray, because it's doesn't I mean it's basically a part of the subset of the subarrays of the particular array, which sums to k, right? So then we have to capture that differently. So okay, so here I explained how how we construct the prefix sum map, and then how that map is used to find the number of subarrays which sum to k. And here I just explained that one peculiar condition in which the prefix subarray which is basically starts from the zero itself, whose sum is represented by the prefix sum itself has sums to k, or number of ones the in that subarray is k, that will capture separately. Okay, so now there's all this in context, right? I think we are in a, I think we are already quite deep in the video, and I am not even started with the description of the main problem. So now let us look at the description of the main problem and what the main problem wants for us, and then I'll explain you why I have like told you this long story without even coming to the problem. Okay, so what does the problem want? So given an array of integers nums and integer k, a continuous subarray is called nice if there are k odd numbers on it, right? So this doesn't look similar to what we have solved till now, right? But notice one thing. So what is the problem trying to say us? Trying to what is the problem asking us to compute is, given a particular array, figure out subarrays in which we have we have number of odd numbers as a fixed value, right? For example, in this subarray, if the fixed value requirement was k equal to 3, then we have, like, this, consider this as 9. So we have 3 odd numbers. So in this subarray, we have like odd number of odd numbers equal to k, right? And then and then we have like suppose we have 4 here, and then in this subarray also we have number of odd numbers equal to k, which is equal to 3 for this particular example. And but notice one thing, we can convert this kind of subarray into a different kind of array, this particular array into different kind of array, and then hence this subarray will also be converted. So suppose we translate all the values which are even to 0, and what all the values which are odd to 1, what will happen, right? Now this eventually, now what we're trying to compute is we're trying to find a subarray whose number of ones is k, which is 3, or a number of subarray whose raised sum or bounded sum or running sum in the subarray is 3, right? Which is exactly what we computed in the previous problem, right? So what we should do, we should basically transfer this very easy transfer of this input array into another array, and then use that to find the subarray sum equal to k, right? And then we have our answer, right? And then all the steps we have already noted. Now obviously I'll come to the code later, but all the other steps we have already like gone through and understood. Now we can do one thing, we can just make a copy out of this input array, but we don't want to do that, because that will consume extra n space, which you don't want to do. So what do we need to do? we'll we only need a prefix sum, right? That is what we need, right? So while computing the prefix sum, we can do that on the fly, right? So for example, we are trying to compute a prefix sum here at this location. We can see that this location is basically an even number, so we can add 0 to the prefix sum, and then populate our prefix map, and the other steps would follow. And similarly, when you come to an element where we have an odd integer, we identify that it is odd. I mean, if you divide by 2, you'll have you'll have one as leftover as remainder, right? And then and then when you find such a number, you just add one to the prefix sum, and then the other steps would follow. That's how this nice subarray, and having notion of this subarray sum equal to k, and specifically the case where the values in the particular array are 0 and 1, would effectively help you to transform this problem into another problem that you already know and solve this. So with this, I have completed explanation of the background of the problem, and why we are doing what we are doing in the code, which I'm about to explain. And now with this background, let us dive into the code, and let us explain the code, what is happening in the code. So this is the function which takes nums as the array as input, and it will return you the number of subarrays which sum to k. We basically store the size of the nums in a particular variable for ease of computation. Then we have then this answer would store the number of subarrays who sum to k. The running prefix sum would be stored in the current sum. This is the map which stores as key the particular prefix sum, and as value a vector of indices where the prefix sum was obtained, right? And then obviously we look at we find if yeah, the value is odd, we go through all the values, and if the value is odd, we add one to the prefix sum. And then if the prefix sum is equal to k directly, then we have no way to look at the map and figure out, because of the limitation of the map, and capture this particular answer, so we capture it before. And then basically we try to find this current sum minus k, right? As I explained earlier, pj minus k, that same thing. Pj is current sum here, current sum minus k, and try to look for if there is a pi which exists here. So this pj minus k would be a pi, and that would be in the map. And then that entire scenario which I explained in the drawings would be valid. And then basically we need for all the indices that are corresponding to the particular key, or all the values corresponding to the particular key, will form one-on-one subarrays which satisfy our condition. So those and entire size, right? Entire size means all those indices would be added to the answer, because that means our subarrays uh, would satisfy our condition. Hence, that is stored in the answer. And then obviously we push this. Will populate the map with the current sum, and push the index where this correct sum is obtained to the map, right? This we can push later, because we're anyway computing the current sum right here itself with the current index. So so that is what is required for this computation, this finding the number of subarrays in which we find the value as current sum minus k. From there we generate the answers that we need to generate. And then once that is done, we obviously have to populate the map, keep populating the map. So that we do in this step. So with this, I hopefully have given you a complete clarity about this problem, about the thought process behind solving this problem, how we break this problem down into some a very specific version of subarray sum equal to k, when all the numbers are either 1 or 0. And then uh, and then uh, and then basically solve the problem. So one more thing that I want to mention before I end this video is, here while adding the answer, we never look at whether the indexes that we have corresponding to this value current sum minus k is less than I or not, because it doesn't have any negative elements, right? So there is no possibility that there will find an I which is like more than this particular I. So it doesn't have negative elements, it doesn't have the possibility, so we don't need to look at that. We can directly sum all the elements in a I think in a classical subarray sum equal to k, we need to look at like whether any of the index is greater than I, and then basically not sum that, if that is the case, right? So with this, I have come to the end of the video. Thank you. Bye. See you in the next video.